So I want to talk a little more about RREF. Judging from the homework, it looks like you guys are catching on to it pretty well. But I just want to touch on a few more problems from the homework. This is problem 17 from section 3.2, and we just want to show the linear independence of three vectors. So we got B1 is 1, 1, 1, and B2 is 1, 2, 3. Last vector is 1, 3, 6. So basically I want to show that the linear combination of these guys is a zero vector if you solve for the coefficients. So of course one way to do that is put those in a matrix. So I put them in a matrix called M here. So we see that these guys, there's B1 is the column 1, B2, B3 is the column 3. And the easiest thing is to just first look at the rank. The rank is full rank, so we immediately know that that matrix is invertible, and so the columns are linearly independent, but it's all the same. And if I do an RREF on that, I see that it reduces to the identity matrix, which is equivalent to that same statement. So those vectors are linearly independent. So using RREF or just using the rank command easily shows that for us. But you should keep in mind exactly what's going on here. What you're doing is you're showing that C1 times B1 plus C2 B2 plus C3 B3. I'm going to solve that, say if it's equal to 0. And so you're really solving that matrix equation again, that this matrix of column vectors from B1, B2, B3. So this all goes back to section 1, systems of equations. Right? Keep in the back of the mind what you're doing. Right? We've abstracted it to looking at just the rank, and and you can just do that in your computer algebra like octave. But you should always keep in mind what's going on with the actual solution of the equations. So what you're doing is you're solving this equation, and it turns out, when you solve this, C1, C2, C3 are all equal to 0, which says these guys, the only solution that produces 0 is when the coefficients are 0, so these guys are linearly independent. So it's just another way of saying that same solution. So we've abstracted those ideas, but always keep in mind that RREF goes back to actually solving a system of linear equations. Okay, so now I want to look at problem 11 in section 3.1. That's on page 110. So I've got a matrix D, and I just want to look at finding its span of its kernel and image space. Right? So we've done that several times now. So here I've defined D in octave. Right? So the same matrix. So first thing is always, since rank is now built into the functionality here, is check the rank. So we know that the rank is 3, so the dimension of the, in our later terminology, the image space is dimension 3 and the kernel has dimension 1. So we're only looking for one vector that spans the kernel. So if I do an RREF on this, we should be able to find that. So this tells me that I've got first vector, second, and the fourth column are my image space vectors, and that I've got a free variable in the third variable. Okay. So what I want to do is then write that in terms here. So basically I'm taking my vector that spans my kernel. Let's see if I can get them both in here at the same time. I don't think I can. So right. That was the third component was my free variable, and the last one I had a 1 in the fourth column, so that was equal to 0, and I had 1 minus 3 in the second row, so the second variable is equal to 3 times the free variable. and I've got 1, 0, 2, so I have minus 2 times. So that should be the vector that spans my kernel. If I look at that, compare that, right here I've got free variable. It's going to be my third, right? So that's the 1 here. Right? I've got x1 is equal to minus x3, so that gives me my minus 2 here. Got x2 is equal to x3 times x3, so that gives me my 3 here. Of course, this is the free variable. And x4, right, there's nothing it equals to, it just equals 0. So remember, you can think of there's a column of zeros over here, and you can actually put that in and I'll reduce it if you want to do it that way too. Right, so 0 is my last component. So my right, this is for the span of the kernel. Using a mouse to do something where I've got a tablet now. Hey, cool. So this is the span for the kernel. And then, of course, we know that the vectors here, this one, and this one, then are the vectors that span the image space. Right? So those 3 vectors would span my image space. Right? Okay, now I want to look at problem 23 in section 3.3 on page 133, and I called this matrix N, and we want to find the basis of the kernel and the basis of the image space. Well, if you notice, the matrix is exactly the same matrix that I just called D a minute ago. It's the same, exact matrix, except now instead of my terminology's changed. Instead of trying to find the span, I'm trying to find the basis. What's the basis? It's just the minimal set of linearly independent vectors that span that particular set, that particular vector space. So it's exactly the same problem that I just did. So we know that this vector, and this vector span the image space, right? And that the vector v1 that I just saw for a minute ago, right, equal to minus 2, 3, 1, 0 is my basis vector for my kernel. So these 3 columns are the basis vector for my image space, and this vector is the basis vector for my kernel. And in terms of the next section, right, we know that this is a 3-dimensional vector space, and this is a 1-dimensional vector space, right? So all the vectors that are multiples of this get mapped to 0, and then everything else in the image space has to be a linear combination of these guys. And of course, the Kyle numbers, you can write those up here. This combination is really, right, minus 2, 3, 1, 0. And if you multiply this by minus 2 and this by 3, you'll get this vector right here. So in other words, this guy is, according to the Kyle numbers, the redundant column vector. So if you happen to just see that relationship, that if I multiply this by minus 2 and this by 3 and put them together, I get equal to this particular column, then you could just write the Kyle numbers out the top, and then that would just give you the components of the kernel basis vector. Right? But I just prefer that I think it's imaginative if you can do that, and good skill, but RREF always gives you a nice methodology for attacking these problems. So I would do it that way. Okay, so now I want to look at problem 11 in section 3.4, right, where you want to write a vector x as a linear combination of v1 and v2 essentially. But what you really want is, in our new terminology, is to find the coordinates of x relative to these basis vectors. Okay, so first we have to make sure these guys are linearly independent, but that's fairly easy with RREF again. So here I've input. Right? So my column here is V1, column 2 is V2, and here's X. Right? Why am I doing that? I'm solving for a combination of these guys equal to this guy. So this is essentially an augmented matrix with these two vectors and X. Right? So it's really the same thing we've been doing, just in a different description. Right? So if I reduce it, right, I get that these guys reduce ones along the diagonal, so that it says that V1 and V2 are linearly independent, and that I have coefficients of 1/2, right, to get X. Right? So let's go back and consider how that relates to what we're doing here. Right? What we're really solving for again is that same, right, C1 times V1 plus C2 times V2 is equal to X. Right? And we saw that C1, if I wrote this in terms of a matrix equation, which is what I just did with the RREF essentially, and what is it, minus 3, 2, 3, right, times C1, C2, I want that to come out to be equal to X, and so I've got, I solved it, and by my RREF, saw that C1, C2 was equal to 1/2, 1/2. Right, let me bring that back in here and compare. Right, so all this is these guys, this last column over here. So I've essentially used, right, I've augmented this matrix, right, with X, and solved it and found, C1 and C2 for this linear combination. So again, I'm solving a system of equations. Right? It's just underdetermined. So, except now in our new terminology, right, the coordinates of X are relative to this vector V, this basis V1, V2, are 1/2, 1/2. In other words, if I sort of made this into a coordinate system, drew these out in 3 space, I didn't have to go 1/2 unit along the V1 direction plus 1/2 unit along the V2 direction to get to and add those together to get my vector X. Right? So it's just new terminology for essentially what we've already been doing. But why would we do that? Well, what we're really aiming for is to be able to go back and forth between different coordinate systems. Right? If you're on the space shuttle, you don't want to think in terms of absolute coordinates relative to Earth. You want to think in terms of coordinates relative to your position inside the space shuttle. Right? I want to move forward 6 feet. I don't have to figure out that in terms of Earth coordinates. Right? Those kind of things. So that's the long-term goal for all this stuff. But right now it should be a lot of terminology. But again, you can relate this all back to RREF and solving systems of equations. Just keep those things in the back of your mind.